let's try to understand the continuity equation. This continuity equation is very important in electrodynamics. This is very important in electrodynamics. And this continuity equation tells us about the conservation of charge. Conservation of charge. And we know conservation of charge is something fundamental in nature. This is fundamental in nature. And there are actually two uh, two important conservations of charge. One is called the global conservation. Global conservation of charge, which says that the charge of the universe remains constant. So this talks about the universe charge. The total charge of the universe remains constant. But we are not interested in that thing. The continuity equation doesn't actually, it's not related to that thing, but it tells us about the local conservation. Local conservation. And local conservation of charge says that if we have some region, if we have some region, and there is a change in charge, change, or I should say variation in charge, then there is only one possibility, that either the charge is coming out through the surface that encloses that region, or like the charge is coming into the region through that surface. So this is some region, and if we have some charges there, q1, q2, q3, q4, and we're seeing that in this region, the charges are actually varying. So there is variation in the charge. So there are only two possibilities, that either through the surface charges are coming in, okay, or charges are going out. Because when I say that there is the change, I mean it might increase in the region, or it might decrease in the region. In case the charge is decreasing in this region, then the charges are going to come out through the surface, that actually encloses the volume, the region. And if there is an increase in the charges, okay, there is increase in the charges, then there is only one possibility, that the charges are coming in through the surface. The continuity equation tells us about this local conservation of charge. I hope you understand the basic definition, and what is the continuity equation tells us about. So a continuity equation tells us about the local conservation of charge, and we're actually interested in the local conservation of charge, because whenever we are dealing with the system, so we are locally involved into that. So let's try to formulate it as mathematics, and then we will come up with some equation, very important equation, which we call the equation of continuity. So let's make some region here. Okay, this is some region, and we have some charges there. We have some charge there, and q1, q2, q3, q4, q5, q6, q7. So there is a whole lot of charge there, and let's say the amount of the charge per unit volume is rho. So rho is dq by d tau. So charge, how much charge is present in volume. Let's say there is some region, some small region tau t, and there is the charge amount, how much is dq, is the amount of charge in that region. And let's say this is the 1 centimeter cube volume. And so if we define the charge density, so actually it is a volume charge density, which is dq by tau t. And so we can write, which implies dq is equal to rho tau t. Okay, so which implies q is actually integral rho tau t. This is very important equation. This is very important equation. Let me close it here. So this is the charge. Now this charge is actually varying. Now there is the variation in the charge, let me write the variation. So let me write it let me write it capital. Okay, let me write it capital. I'll uh, tell you why. So let me write it capital because you might confuse with this thing. Oh, so this is a different total charge. This is actually the total charge in this volume. This is the whole charge in this volume because we wrote it in terms of the volume charge density into the small volume, and then we integrate the whole region. We integrate this whole region. So that will give us the total charge in the region. Now this charge is varying because the continuity equation tells us about the variation in the charge. So that is dq by dt. This is the variation in the uh, uh, charge in that region, and we can write that as integral dou rho by dou t d tau. And remember, this is the time and this is volume. You understand? So this is actually the volume integral. This is actually the variation in the charge inside the region. And if this is variation in the charge inside the region, let's say it's decreasing, so the charge must come out through this surface. According to the conservation of charge, the charge must come out through this surface. Now, if charges are moving and they are coming out, so that will contribute current. Okay, now I'll use a different pen here and see. Now we know the volume current density. Volume current density. How do we define the volume current density? We define J equals di by dA perpendicular. I hope you know this definition. It is how much current is coming out through some perpendicular surface. Let's say this is the perpendicular surface here, and this is the di, and this surface is dA perpendicular. That area should be perpendicular to the current, and here we will define J equals di divided by dA perpendicular. Okay, so which implies di is actually J dA perpendicular is actually the dot product, because we know this area vector is it's a vector quantity. We call it as an area vector. We call it as an area vector. So this is dA vector, and since J dot dA will give us the current. Now how much current is coming out through whole the surface, we have to integrate. So which implies di, integral of di is integral of J dot dA perpendicular, because this is the closer surface that encloses the region, so it is actually the closer surface. That's why I wrote the closer surface. Now, according to the equation of the continuity, the charge variation inside with respect to time is the current coming out through this enclosed surface. So that means this must be equal to this thing. Okay, so let me write it now, which implies closed integral volume dou rho by dou t d tau equals closed surface integral J dot dA perpendicular. But remember, since this is the volume integral, this is the surface integral, we can use divergence theorem. Divergence theorem. And divergence theorem converts the surface integral into the volume integral by taking the divergence of that vector quantity. So which implies volume integral dou rho by dou t d tau equals volume integral del dot of J d tau. So it's a volume integral. Now since both are the volume integrals, so this integrand must be equal to this integrand. Okay, so which implies dou rho by dou t equals del dot of J. This is actually the continuity equation, but I must tell you very important thing, because the charge inside is actually decreasing, so we will take the negative sign. This has a negative sign. We could actually take the negative sign from the very beginning, but I thought let's take it at the last. Okay, So this is the negative sign here, because the inside charge is actually decreasing. It's actually decreasing. So this is the, or you can start from here. There is no problem in that. There is no problem in that. Okay, so this is the continuity equation. Thank you so much. Thank you for watching.